All right, so in 7.1 part 1, or 7.2 part 1, we had just started learning about what the graphs of inverse trig look like and the domains and the ranges. So if you remember a little bit, when we looked at 7.1, I graphed the sine function, and I asked you if it passed the horizontal line test. Okay. Does that pass the horizontal line test? No. Which means if it fails that test, then the inverse is not a function. And that was a problem. Because when we deal with inverse sine, we want it to be a function. So that way when you do it on the calculator or somebody does it somehow, we all get the same answer. If something's not a function, that means there's multiple answers. We didn't want that. So we ended up limiting where we looked at inverse sine, and we did like negative 90 to 90. Right? And that made it so we were just looking at this section right here. And that worked perfect. Cosine, we did something similar, and inverse tangent, we also did something similar. What we're going to look at in this part is we're not going to be looking so much at like what the domain and the range is, but we're going to look at how we can take a formula like that and get rid of all the trig. So when you're done, all you have is an algebraic formula, like x squared plus x divided by 2, or something like that. So we'll get to this, but there's a way you can convert that to straight algebra with no sines and cosines in it at all. Now, you can't do that for just any trig equation all easily, right? But there are some that you can. And that's what we'll start off talking about. So when you're asked to write an algebraic expression from a trig expression, that means when you're done, you don't have sine, cosine, tangent, secant. You don't have any of that in the final answer. You can have plus, you can have minus, you can have square root, division, x's, you can have all that stuff. Anything you'd see in algebra, but not sines and cosines. So the way I'm going to do it is I'm going to start on the inside of my formula and work my way out. That's going to be how we do it. And after you do a couple of these that have the same pattern, and by pattern I mean, I'll come right back to that. Regular trig function, inverse on the inside. Regular trig function, inverse on the inside. All right, that one's a little different. But regular trig function, inverse on the inside, they're all going to be the same pattern in how you solve it. All of them. So we're going to start with the inner trig function, and we're going to try to set up a right triangle diagram. Okay, the diagram is basically to help you visualize what's opposite and what's adjacent. Some people might be able to do that kind of in their head. Okay, but one thing we are going to use here is the definitions of sine, cosine, and tangent. So remember, sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. Now, if the inner trig function has inverse trig, right, like the first two that I'm going to do with you, it helps to rewrite that with regular trig. And I'll show you how we do that. That step's very, very simple. A couple things you can keep in mind when we go through this process is Pythagorean theorem. That'll work for some problems. And that's pretty much all you need to think about. Pythagorean theorem. Okay, so I'm not going to write down any more detailed steps than that. we're just gonna go through a problem, and first time through it's probably going to be a little not make the most sense, but then we'll do it a second time. All right. Now the letter they use here doesn't matter at all. That's just the argument, and they're using V. Sometimes you'll see V, you might see U. I guess you can see X, you can see Y. It doesn't matter. Right, so when I am done, I want to have a formula in that box that's pure algebra. No sines, no cosines. Right. So the directions said to start with the inside or with the outside function. Which one? Inside. Inside. Okay. Now, That's an inverse trig function. And then I also said, if the inner function contains inverse trig, we're going to rewrite it. And I'll show you how we rewrite it in a second. All right. When you do inverse trig, right, like when I go on my calculator, and I type something in like inverse sine of 0.2, right? I get 0.201. What is that 0.201? It represents what? What do you always use inverse trig to try to? So think back to when we solved right triangles. You used it when you had to find the angle. You used Pythagorean theorem when you had to find the sides. We used regular trig when you had to find the side. But we used inverse trig when you had to find an angle. So when I do this, that's going to come out to an angle. Let's just call it theta. I don't know what the angle is going to be, but if I do inverse cosine of v, whatever v is, the answer will be an angle. We're not going to know what that angle is. Now, what function cancels out inverse cosine? Cosine, regular cosine. That's how I'm going to rewrite this. I'm going to take the cosine of what's on the left, the cosine of what's on the right, and now I have this. V equals cosine theta. So before I had inverse cosine V equals theta. Now I have cosine theta equals V. I just rewrote what was on the inside a little bit. And now I want to draw a diagram for that. I want to draw a diagram and try to make this situation happen in the picture. Okay, let's draw a right triangle. You can put theta wherever you want. Doesn't matter if you put it at the top or the bottom. Okay. What's the definition of cosine? Yep, adjacent over hypotenuse. So in that diagram, I need you to label the adjacent and the hypotenuse so that when you divide them, the answer comes out to V. Because that's what it says it should be. If you do the cosine, adjacent over hypotenuse should come out to V. So there's lots of ways you can do it, but anyone think they can give me the simplest way to give a name to the adjacent, give a label to the hypotenuse, so when you divide them, you get Yep. You could, yep. So where would you put the 2V? Adjacent. And where would you put the 2? Yep, so you could do that, that's fine. Because if you take adjacent and divide by hypotenuse, you will get V. We could even go a little bit simpler than that. Yeah, I could, if I just made this V, and I just made this 1, adjacent divided by hypotenuse is now V. So what we've done now is we've set up a picture that basically represented this. Okay? Now, they want to know the sine of what we just created a picture for. Okay? So the part that I circled is the picture. They want the sine of the picture that I just drew. Now, sine involves which two sides? It's opposite over hypotenuse. Well, I've got hypotenuse, so I could actually fill that out right now. But I don't have opposite. Okay? Just call it x. How could I figure out what the opposite is in terms of the other two sides that I already know? What would be your, so what would you set up? Yeah, set up the Pythagorean theorem. 1 squared equals v squared plus x squared. Now solve for x. And when you're done, you're going to have something with 1s and v's in it. And that's going to be this side. So in a minute, I'm going to erase that x. So 1 squared gives me how much? 1. V squared. What are we going to do with the v squared to start to get x by itself?
I would subtract.
Subtract it. And now that would be x squared, but I want x. Square root it. So that opposite side is the square root of 1 minus v squared. Square root of 1 minus v squared. Now I've got my picture. I had the 2 sides labeled from the original, and I got the third side using Pythagorean theorem. Now, go back and look at the outside function, sine. Opposite over hypotenuse. Square root of 1 minus v squared over 1. Which, we can just simplify that to the square root of 1 minus v squared. So if you wanted to take the sine of the inverse cosine of something, you could just do this instead. The square root of 1 minus v squared. Let's check it. The way I could check it on the calculator, type both of those in and try some different numbers and see if they come out the same. Alright, so we got sine, inverse cosine. Remember, I can't use v, I have to use x. And let's do the square root of 1 minus x squared. Now, does anybody remember for inverse cosine, you can only plug in certain numbers? Anyone remember what the numbers have to be between for inverse cosine? Yeah? Yep, 1 and negative 1. So, if you try something like this, well, that's not going to help. But let's try 0.2. y1 and y2 gave me the exact same answer. y1 was the original problem. y2 is the formula we came up with. Right? Let's try another one. Let's try 0.6. They both come out to 0.8. Let's try negative 0.7. They're both coming out exactly the same. So what we just did is we converted something that had trig into something that doesn't. Any questions on the steps for that version? Right, we're going to try kind of the same kind of thing again. Right, let's start with the inside. Set it equal to theta. Rewrite it in terms of regular trig, and then draw a diagram. And then from there, figure out your third side, and then look at what they want to know. Do they want sine? Do they want cosine? Do they want tangent? Do they want secant? Once you got all 3 sides in the triangle, you can find anything you want. What else could happen? What could happen with the square root, even though it didn't happen in this one? It could end up in the bottom. If it ends up in the bottom, just make sure you fix it so it goes to the top. Okay, so let's try this one. The cosine of the inverse tangent. So when I'm done, I don't want to see any trig in the final answer. Square roots, squares, fractions, subtraction, addition, yep, all that's fine. Okay, so following what we just did, what would be my first step here?
Solve it.
You would rewrite the inverse tangent.
Alright, so yeah, take the inverse tangent. And what should we set it equal to? Theta, right? Because whatever's inside here is an angle. I'm just giving a name to when you do inverse tangent, what you're going to get. Alright, so now inverse tangent of x will equal some angle we don't know. Alright, and now Maddie, what'd you say to do from there?
We would take tangent on both sides.
Yeah, and when you take the tangent of both sides, what would be alone on the left?
X.
And on the right you would have?
Tangent of theta.
Tangent of theta. Okay, so now we have x equals tan theta. What's my next step that I'm going to do with that? Right, we're going to draw a picture and set it up so that when you take the tangent of what's in your picture, the answer is x. So now we have to figure out what two sides are involved. Opposite over adjacent. And there's lots of ways to do it. I would pick the most reduced way you can. So what could we make the opposite? Yep. And what could we make the adjacent? There you go. Ones come up a lot when you do this. I know before we had said, well, we could do a 2, and that would have worked fine because it would have reduced in the end. But I would start out like that. You have to pick any two values that you want so that when you do opposite over adjacent, you get x as the answer. Because the tangent is opposite over adjacent. And this says tangent equals x. So fill in anything you want there, anything you want there. But when you divide them, it has to come out to x. Now, let's go back up and see what they want to know. They want the cosine of the picture we just drew. So what's cosine? Adjacent over hypotenuse. Okay, we've got adjacent. We don't have the hypotenuse. We have to find it. How do you get the hypotenuse? Pythagorean theorem. So it's going to be x squared plus 1 squared. Add them up, and then take the square root. Questions on how I got the hypotenuse? So like x squared plus 1 or something minus x squared, or what do we have, like 1 minus v squared? Those are the kind of patterns you always see in these problems. Okay. Square roots, and then usually something squared plus 1 or minus 1. Okay, so now we can take the cosine of what's in that picture. Okay, what side is adjacent? 1. And what's the hypotenuse? Yep, square root of x squared plus 1. Now on a test you wouldn't see that, even though that's algebraically that would work. I want to fix it so the root isn't in the bottom. Can somebody tell me what do you get if you fix that so the root's not in the bottom? Yep, square root of x squared plus 1 over x squared plus 1. So that's the algebraic formula for doing the cosine of the inverse tangent. And that never changes. If you want to do cosine of inverse tangent, that's always the formula. But these aren't really formulas we memorize because I can ask you, I guess it could be, I could ask you up to 36 different versions of that. Because I can pick 6 different things here. Sine, cosine, tangent, secant, cosecant, cotangent. And then I could pick 6 different trig functions here. So that's a total of 36 different options I have to pair the 2 trig functions. So you just figure out whichever one they ask. Questions on that one? Okay, so we focused on regular trig on the outside, inverse on the inside. Let's switch it. Inverse is on the outside. Regular trig is on the inside, but this time it's an actual value. So when we're done this problem, we're going to have a number for the answer. And if they're asking us to do it without a calculator, what that would mean is on the test, I want to see how you did it. Because yeah, you could just type that in and get the answer. But you'd have to show me how you did it. And it must come out nice. Because if this was a decimal, we'd never be able to figure it out without a calculator. Okay, so where do you think we're going to start? The outside or the inside? The inside. So we're going to start with tangent of 3 pi over 4. And I'm going to see if I can figure that out. Yep, it might be helpful to think of that as 135 degrees. Pi over 4 is 45 times 3. So 45 times 3 is 135. And now 135 is something special. It's a multiple of what number? 45. It's a multiple of 45, and that's how we're going to be able to figure this out. Okay. If this came out to like 137, no. You're not doing that without a calculator. Okay. So there's a few different ways you can try to think about it. Let's try it this way. See if this makes sense. Here's 0, 90, 180. Where's 135? It's in quadrant 2. Can you be a little more specific? Right in the middle. So let's make a triangle right at 135. Okay, what I want to do, I need a little more space, so I'm just going to draw that triangle off to the side, bigger. Okay. What, well, tell me about that triangle. I mean, it's a right triangle. What else?
45.
It is. It's a 45, 45, 90. It's 45, 45, 90. Now, what I have to do to figure out the tangent of 135 is label the sides of this triangle. And remember, you always work with this angle right here, and there's a name for that. Does anyone remember what we called it? The angle between the hypotenuse and the x-axis. And if it was down here, it would be this angle right there. If it was over here, it would be that angle. And if it was over there, it would be that angle. It's your, begins with an R. What is it? Radicand? No, not radicand. There are going to be some radicands in this when we label these sides, though.
What's the second one?
E. Reference, yes. To reference angle. So, that's your reference angle, okay, for 135 degrees, right? So we're doing everything from that angle. Now, in this problem, it wouldn't really matter if you did it from this angle, because that's 45 degrees too, okay? But for future reference, use that angle right there. So we need to label the sides, okay? It's an isosceles. It tells us that two of the sides are the same. So what would be some nice simple numbers to pick to figure this out? 1. And how about this side over here? 1. And how about the hypotenuse now? Square root of 2. Remember, trig functions don't depend on the size of the triangle. If you did 3, 3, and square root of 18, yeah, that's fine too. But it's easier if you pick smaller numbers. Now, technically, this number brought us left, right? Left and up. So this is really what kind of number? It's really like a negative. So we should put that in so we don't forget. I know it doesn't make sense to think of length as negative, but you want to think of the negative as a direction, left, and the positive one is fine. Okay. Now, by writing that as a negative, that's what's going to take into account it's not a 45-degree angle. It's 135 because you went left. If you put a negative and a negative, that would be left and down. That would take into account it being a 225. Okay? So as long as you take into account positive and negative, that's how you adjust for being in another quadrant. Okay. So now, what's the tangent of 45 in that picture? What is it? Negative 1. Okay. Tangent's opposite over adjacent. So that's 1 divided by negative 1. So the tangent of 135 is negative 1. Any question on how I got that? Okay, so now that we have that, we've reduced this problem to this problem. I want to know the inverse sine of negative 1. Okay. Now, think about inverse sine for a second. Anytime you do inverse trig, the answer is always what? You're trying to find an angle. Okay, so the inverse sine of -1 is an angle. Whether you do it in degrees or radians, that doesn't matter. But the answer is an angle. So let's do what we did before. Inverse sine of -1 equals an angle. For me, it's helpful to think of that without inverse sine. Rather, think of it with regular sine. So what could I do on each side to get rid of inverse sine? Do what? Do what with sine? Multiplying you can only do with letters and numbers. You can't multiply with a function. Chris?
Do you take sine?
Yep, take the sine of both sides. Take the sine of what's on the left. You should put on my guess. Take the sine of what's on the right. So this is what you're trying to figure out. What angle could you take the sine of and get -1 as an answer? That's what I'm asking. What angle could you take the sine of and get -1 as an answer? So what's another way that we've thought about trig functions besides just writing equations? We've also done what? Another way to kind of view them. Like, let's say somebody was not really equation oriented. They look at equations and it confuses them. So besides an equation, you could show this as a what? A what? A picture. So let's draw that. Let's draw sine. So remember what sine looks like. Looks like that. What's the highest and the lowest that it goes? 1 and -1. That's why we're going to be able to figure this out. Okay? If it said, where does the sine equal 0.67? Well, you're not going to be able to figure that out by hand. But 1 and -1 is easy to figure out. You just need -1 now. So this is 1. This is -1. So it hits -1 right there. We just need to know what the x value of that is. How far through the cycle of sine are you?
3, 4.
You're 3/4 of the way through. And what is that? 270, or in radians? 3 pi over 2. Yep. So theta is 270, or 3 pi over 2. Okay, so to figure that out, we're piecing together lots of different things we've done. We're thinking about it graphically, rewriting inverse sine using regular trig, a little bit of a circle diagram, and then the fact about isosceles triangles and two sides being the same and kind of figuring it out. So there's lots of things we kind of put together there. Okay. But the answer is 270 degrees or 3 pi over 2 radians. Okay. Any question on that one? Okay, so as we keep kind of going on in trig, I think that's probably the hardest part, is tying together all these different facts that we've learned. Okay, but that's what we're going to keep doing, just kind of pulling from different things we know and see what we can figure out. Okay. Let's look at this one. The cosine of the inverse tangent of a half. Regular on the outside, inverse on the inside. That's what you just did right here. The only difference is, in this one, you don't have to work with a letter. You have an actual number for x. Okay. So when you start labeling the sides of the triangle, you're not going to have an x. You're going to have all numbers in the triangle.
Can't you just take the answer from that one and then plug in the half for x?
Yeah, you could, because this is cosine of inverse tangent. So if we go back, we already have a formula for cosine of inverse tangent right there. So yes, if you had that set up on the test, I would just use the formula, plug it in, and you're good. What I'm going to do is I'll do it with the actual numbers, just in case you didn't have that formula to start with. But it's going to be almost the exact same problem. Yep, that's good. Good that you noticed that. Okay. So, yeah. Maddie, where do we start? Inside or outside?
Inside.
Yeah, inside. So we're going to write inverse tangent of a half equals theta. Now, I'm never going to figure out theta in this problem. I don't need to. I'm going to draw a diagram, I'm going to do some other stuff, but I will never actually know what this angle is. Okay, what do I do after I have that?
Take the sine, both sides.
Yeah, take the tangent. Whatever function you have, do the inverse. So take the tangent. So now the tangent is equal to a half. Okay. These two are exactly the same thing. It's two ways of saying the same thing. Now, what do we do after we have that equation right there? Yep, we're going to make a diagram. And at this step, some people might be able to visualize, okay, that's going to be there, that's going to be there, the hypotenuse is there, okay, they want to know this. They can kind of do it in their head. But if not, sketch it out. What two sides are going to be involved? Opposite and adjacent. And how long is the opposite? And the adjacent? 2. And the hypotenuse? Square root of 5. So it's exactly like what you did in the last problem, 2 problems ago, except you don't have an x. You have actual numbers. 1, 2, square root of 5. Now from here, just go back up and see what they want to know. Cosine. This is the diagram you just drew. Find the cosine of your diagram. What's the cosine? Adjacent over hypotenuse. When I do that, what would my final answer be? 2 square roots of 5 over 5. Now, let's do it. Was it you that mentioned we already had the formula? We could just plug in a half?
Yeah.
All right, let's try that and see if we get the same thing. We should. So, 2 square roots of 5 over 5. Okay, let's just remember that. All right, so we should be able to plug in 1/2 there and see what happens. All right, square root of, what's 1/2 squared? So 1/4 plus 1 over 1/4 plus 1. Okay, what's 1/4 plus 1? 1 1/4 or 5/4. So square root of 5/4 over 5/4. How do you divide by a fraction? What do you do instead? Multiply by the reciprocal. So that's 4/5 times square root of 5. I'm just going to write it as 2 separate square roots. Square root of 5 over square root of 4. And what's the square root of 4? That's 2. 2 goes into itself once. 2 goes into 4 how many times? Twice. So that's 2 square roots of 5 over 5. So yeah, you get the same answer. Just a little bit of arithmetic to simplify it. In general, which one do you think is more useful? The formula with the x's? Or the formula that has 2 square roots of 5 over 5 is the final answer? Like if I asked you to do more of these kinds of problems.
The first one with the X.
Yeah.
Because then you can keep using it.
Yeah, you could just keep using it. This tells you nothing. If I just tell you 2 square roots of 5 over 5, it doesn't actually tell you how I got it. But if I give you this formula, then you can just keep using it over and over. Just change x to whatever you need to change it to. Okay. All right. So we got that. Okay. Let's see how many. We don't have much left, so we'll try that one. Let's see if we can jump right to the diagram. what two sides would be involved, and if you can't jump right to the diagram, that's fine. Just do what I did in the last problem, write out each step. But what two sides are going to be involved? That'd be cotangent. Opposite and hypotenuse. How long is the opposite? The hypotenuse? 2. And what about the third side? Square root of what? 3. Yep. Because if you square that, you get 3. If you square that, you get 1. If you add 3 and 1, you get 4. And the square root of 4 is 2. If you're not sure how to get square root of 3, you could go to Pythagorean theorem. Okay, so we just cut out a couple steps. And now we can jump right to the final answer. Cosine is what over what? So I want the adjacent over the hypotenuse of that picture that I just drew. So what would my final answer be?
Square root of 3.
Over 2. Yep. And this is also something that the calculator can't give you exact. Like if you try to type that in, you type in cosine of inverse sine of 0.5, it's going to give me a decimal, 0.866. Well, there's all kinds of decimals it could give me. I can't memorize all of them. So that way we just figure it out the way I showed you, and you'll always get the exact answer. Okay? Square root 3 over 2. You can try to convert 0.866 to a fraction using math fraction. It won't be able to do it. It can't change. If a number has a square root in the fraction, it can't do it. If it had something like just 0.25 and you try to convert that to a fraction, yeah, that will work. But there can't be a square root in the fraction for that. Okay. Questions on that? Okay. All right, so last thing we'll look at, which is a little bit of a review. But remember that when you're solving a trig equation, if you find one solution, then there are infinitely many solutions. Okay? So like when they ask you to do that, what do we usually have to add on to the end of our answer to show that the answer repeats? Right, you have to put plus the period times n. Whatever the period is. If it's 2 pi, you put 2 pi n. Right? But that's how you show that it repeats over and over. Okay? If I ask you a question about like secant, cosecant, or cotangent, you don't have a button for that. The only way to type it in is to flip it. Any questions about which trig function you have to flip to type in like secant, cosecant, or cotangent? All right, so let's try a couple examples. So, the first one says sine of x equals 0.6. And they're looking for all solutions. So, if you kind of think about it and visualize it in your head, can anybody tell me how many solutions you're going to get per cycle? Think about what sine looks like. Think about a horizontal line at 0.6. 2. Sine looks like this. This is 1 up here, so 0.6 is maybe like right there. You're going to get 2 answers per cycle. Okay? Now, what we have to know though is what's the cycle? What's the period of just sine that's like 1x? Anyone remember what's the formula we use to find the period again?
Well, it's 2 pi.
2 pi over, in general, b.
Oh.
That's the formula for sine, cosine, secant, cosecant, if you have to find the period. That is not the period for tangent and cotangent. We'll talk about that after. Okay. But that's the period for sine, cosine, secant, cosecant. B is the number in front of x. So in this case, it's a 1. So Jake told us the period is 2 pi. So that means on the end of each answer that I'm going to use my calculator to find, what's going to be put on the end? Plus what? Plus 2 pi n. Okay. Now, how do I use my calculator to get 2 answers that are going to go here? What do I have to do first? Let me clear out anything else I have. Okay, and so the first thing you said, yeah, you got to graph it. This one's pretty straightforward because you have a button for the trig function. 0.6. What else before I hit graph? What should I set my window to? So it's not confusing. Yeah, I would go 0 to 2 pi, so you're only looking at one cycle. Okay, you don't want to be looking at more than one cycle. So anything that has a difference between 0 and 2 pi is good. How about my min and max for the y? Yeah, it's only going to go 1 to -1, so -4 to 4 is fine. Okay, so there's one cycle, and there's 0.6. And my last step from here? Yeah, we're going to go second, calc, intersect, and let's just get this first answer. And remember, you're solving for an angle. The sine of what angle is 0.6? 0.64, we'll just say 0.64 radians. Okay. Now, let's see if we can get the other answer. Okay, because we're gonna have to do this eventually without the calculator. What trig function are we dealing with in this problem? Sine. And we're looking for where sine equals a positive or a negative number? A positive. Remember, this is 0. This is 1.57 or pi over 2. It's 180 or pi, which is 3.14. And that's 270, or 3 pi over 2, which is 4.71. 0.6, all right, or 0.64. That answer is in which quadrant? First one. So where would you expect your second answer to be? Yes. That's the other quadrant where sine is equal to a positive. If you go down here, you're going to get negatives, right, for sine. So we're going to be in quadrant 2. 0.64 is your reference angle. Does anybody remember what the formula was in quadrant 2? If you know your reference angle, what do you do with it? Minus it from 180, yes. So take your reference angle and subtract it from 180, or in our case, pi. What was it? 0.64. And we get 2.50. Let's do the intersect and see if we get the same thing. Just double check it. Should be about 2.50. And rounding it is. We rounded 0.64, so that's why that's rounded too. But that does round up to 2.50. So it depends on what quadrant you're in, but if you're here, the answer is your reference angle. There's nothing you have to do. Here, it's pi minus the reference angle. How about in quadrant 3? Yep, it was pi plus reference angle. And what about quadrant 4? Yes. So using ASTC, that'll tell you where things are positive and negative. And then these will tell you the formula. So you have to use the ASTC to figure out the quadrant and then go from there. Okay. How about cotangent x equals 2.5? Before I do it, I just want to visualize how many answers per cycle here. Yeah.
2. Oh wait, that one. Down.
1.
Yeah, there's just one. Because cotangent looks like this. Each one of those is its own cycle. When you put a line at 2.5, between those dotted lines, those vertical asymptotes, that's a cycle. So you're only going to get one answer per cycle, which means you don't have to do any of this stuff. Okay? This is if there's a second answer. You figure out the quadrant and then use the formula. For this one, there's only one answer. Okay? So we're not going to have to worry about any of that. What do we need to know? The period. What's the formula for period of cotangent? Pi over b. Yep. And in this case, what's b? 1. So the period of that is pi. Now, they didn't specifically ask for the period, but what they did ask for is to find all solutions. So what are you going to put on the end of your only solution? Plus pi n, yes. Now we just have to graph it and see what it is. Vinny, how do I type in cotangent since I don't have a button for it?
1 divided by
1 divided by tangent. There we go. And we're going to see where that hits 2.5. Now, if you set it at 2 pi, you're going to see 2 cycles. Let's just set it at 1 pi. And you should see, oh, I had the curve. That's the curve for tangent I drew on the board. Sorry. That's cotangent. It goes the other way. But either way, same reasoning. You get one answer per cycle. And to find it, just see where that goes. Second, calc, intersect. Should be good to just hit enter right away because you shouldn't have a problem with that. 0.38. And that answer will repeat if you add and subtract 3.14 to that over and over. Okay, any questions on that? Okay, so the last part, a little bit of a review, kind of finding those trig functions, but the first part, converting trig to algebra, I think that part, that's new.
So you know how you showed us on the like the last one where there was 2 answers and you found the second one without a calculator?
Yep.
How would you find the first one without a calculator? Or
Without a graphing calculator?
yeah.
I can't do it without a calculator, but I can do it without a graphing calculator. Just take the inverse sine of each side. And x is the inverse sine of 0.6.
Okay.
But that's still a messy number I would need a calculator for. Any other questions? Okay, and the reason I showed you guys how to do that is because eventually, especially in calc, you won't be allowed to use a graphing calculator to get those answers. So if you know that ASTC chart, that's how you get around using a graphing calculator. Okay, so homework is on 394. And it's 37, 38, 41, 42. and 44 to 53. That's it. So we'll take a look at that tomorrow. And you guys have just under 20 minutes or so left. If you want to start anything, I got some extra books. If you need to ask me anything about makeup work or anything, just come on up and we can take a look at what's going on.